Let's try to find the Maclaurin series for this function, 1 over the square root of 4 minus x. One way to find the Maclaurin series is always possible, that you're always allowed to do, is you could just use the definition, right? So f of x is equal to the sum, and goes from 0 to infinity. I should be very careful here and call this by a different name. So let's call it t of x for the Taylor-Maclaurin series. But you can always just plug into the definition and take the n derivatives applied at 0 over n factorial times x to the n. Right? So this is the definition. And as long as you can find a formula for the derivatives evaluated at x not equal to 0 or x equal to 0, and you can write this down, then you're good to go, right? This is fine. There's nothing wrong with it. But for this one, let's use something that we've just recently learned, which is the binomial series. And so the binomial series applies when you have a function of the form 1 plus x to the power k, right? And so this is equal to the sum, n goes from 0 to infinity, of these terms, the binomial coefficients, sometimes read as k choose n, x to the power n, and this one converges. We're told that this converges between x equals -1 and 1. We're not, so you should work this out, right? You can show this. But the key thing here is that this binomial coefficient is equal to this product, right? K times k minus 1 times k minus 2 all the way down to k minus n plus 1 over n factorial. All right, so what we can do is, the first step, if we're going to use the binomial series to write down the Maclaurin series for this function, then the first thing we have to do is get this function in this form, right, before we can use it. Once we do that, then we're going to have to, step 2 is we're going to have to find a way to represent this given our k value, if it's possible. We'll at least give it a try, and if not, we'll just, write it out in some longhand form. But otherwise, but then at the very end, then we'll just try to write it down as nicely, succinctly as possible. So let's get into it. Our function, remember, is f of x equals 1 over the square root of 4 minus x, and that does not look like this function right now. So the first thing we should do is, well, there's a couple different things we could do. We need a 1 in here, right? So let's just do this right now. We need to factor this 4 out and make that a 1. So if we do that, we end up with square root 4 times square root 1 minus x over 4. You got to take the 4 out of everything, right? And of course, the square root of 4 is just a half. And at this point, we can take the rest of this root and move it upstairs, right? And we can write this as 1/2 times 1 minus x over 4 to the power -1/2. All right, we're almost there. We've just, in those 2 quick steps, we've done almost everything we need to do. But notice in our binomial theorem statement up here, whatever this is, right, this binomial statement, that's a plus and this is a minus, right? That's not good. So what we can do, one thing that I like to do, is just make a substitution. Let's let u equal -x over 4. All right, and if we do that, then this series can be written as 1/2 times 1 plus u, right? The minus sign's wrapped up in the u, to the -1/2. The 1/2 in front is a constant, and the rest of this obeys our binomial theorem with k equal to -1/2, right? It's a binomial series with k equal to -1/2. All right, so there's step 1. We're going to be able to write this down, right? So we're going to be able to write this down just symbolically as the following. So this tells us, right, that our f of x is equal to 1/2 factors out, sum n goes from 0 to infinity of -1/2, choose n like this, times u to the power n, and then we go back here and remember what u is, right? So this is 1/2, sum n goes from 0 to infinity, -1/2, choose n, of -x over 4 to the power n. All right, and this can be rewritten as 1/2 sum n from 0 to infinity, -1 to the n can come over here. We have this -1/2, choose n, 4 to the n can also come way over here, and then we have x to the n, and this one converges for x between -4 and 4. I'll let you work out the details, but it's because u's got to be between -1 and 1, right? So, all right, this is great, except like I said earlier, if possible, we want to have a better way to represent this term right here. Okay, so when k is equal to -1/2, can we write down this coefficient in a nicer, more more computer friendly. By computer, I mean a human who computes, person friendly form. So let's try. Let's just make a table here, okay? So remember our k is a half, but let's make a table for the n values. And so we've got n and then negative 1/2, choose n. When n is 0, this is just k. All right, that's it. By the way, k is negative a half. So when n is 0, this is just negative 1/2. All right, when n is 1, we get negative 1/2 times negative 3/2. Subtract 1. Divided by the way, n factorial. So really what I want to do here is make a formula. Let's not forget about the n factorial, okay? This n factorial is part of it, but what I want to do here is I really want to make a formula for the numerator, which is k minus 1, k minus 2, all the way down to k minus n plus 1. So let's see if we can make a formula for this, okay? Which means that I've got this a little twisted, don't I? So in this case then, if this is the formula, k minus n plus 1, then this term is 0, the next term is negative a half, right? And then we work from there. All right, so when n is 2, what do we get? When n is 2, this is the negative 1/2 times negative 3/2, and so that's going to equal negative 1 to the 2 times 1 times 3 all over 2 squared. And then let's go to the next one. So we're looking for formulas like this. This formula might be good, right? So the next one is going to be negative 1/2 times negative 3/2 times negative 5/2. All right? And so this is negative 1 to the third times 1 times 3 times 5 all over 2 to the third. We're starting to notice a pattern, right? Can we write it down yet? Maybe. Let's write one more time here. Negative 1/2, negative 3/2, negative 5/2 times negative 7/2. This is negative 1 to the fourth times 1 times 3 times 5 times 7 all over 2 to the fourth. And now we can start to make our hypothesis here. So for our generic n, what are we going to get? We're going to have negative 1 to the nth power. This is the same. We're going to have divided by 2 to the nth power. This is the same. This is then the product of 1 times 3 times 5 all the way up to 2n plus minus 1. 2n minus 1, right? So this is 2n minus 1. All right. And then what can we do here? Well, this is good, right? But what we can do is we can kind of spread out these terms, actually. And we can try to make sense of this. We've done this before in a previous example, but we can multiply here by 2, by 4, by 6, all the way up to the one that comes before this is 2n minus 2, right? If we multiply through by those, we have to also divide out by those. Here we have, this is by the way 2 times n minus 1, right? So we have n minus 1 factorial times 2 to the n minus 1. There's a 2 from each one of these that can get factored out, has to get canceled. The rest of these terms are 1 times 2 times 3 all the way up to n minus 1. So that's n minus 1 factorial. And that right there then gives us a formula, because this is going to equal we can do it in green. This is going to equal negative 1 to the n over 2 to the n times 2 to the n minus 1 times n minus 1 factorial. And then what's on top is now 2n minus 1 factorial. So there you go. This is almost all of it, right? What did we leave off? Well, remember, we only did this portion, right? We have to now, don't forget, divide through by n factorial as well, right? And so let's try to get this all straight. By the way, here we should write 4 to the n is 2 to the 2n, right? 2 to the 2n. And then what we can do is take this 1/2, put it in here as well. Now we've got 2n plus 1. So we're going to try to combine all this stuff, and let's see what happens. So here we've got our function 1 over square root 4 minus x is equal to the sum n from 0 to infinity. Let's look at everything we've got here. Remember, we need an n factor. Let's write this down first. Negative 1 to the n, 2n minus 1 quantity factorial over 2 to the n times 2 to the n minus 1, which is 2 to the 2n minus 1, right? Over n minus 1 factorial. By the way, there's another 1 over n factorial, right? There's an n factorial on the bottom. So just leave it like this. And then we have to go back and get everything else. So we need negative 1 to the n over 2 to the 2n plus 1. So there's another negative 1 to the n. There's a 2 to the 2n plus 1. And this is all times x to the n. Just make sure we got everything, right? And we then notice what? These two cancel. Negative 1 to the 2n is going to always be positive. What? We got 2 to the 2n minus 1 times 2 to the 2n plus 1. If you add all this up, you get 2 to the 4n, right? 4n plus 1 minus 1. And so let's see what we have. Put this all back together, right? This ends up giving us the Maclaurin series for the function 1 over 4 minus x under a square root equal to sum n from 0 to infinity 2n minus 1 factorial over 2 to the 4 to the power 4n, right, times n factorial times n minus 1 factorial, all times x to the n. And so this comes from binomial series, and this converges, by the way, for x between negative 4 and 4. Exclusive, does not include the endpoints.